Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be talking about what influence temperature can play on whether or not a reaction is favorable or unfavorable. And not too surprisingly, it turns out enthalpy and entropy are going to have a big role to play here. So one of the big things that is worth noting is when we try and find the Gibbs free energy of an individual species, we do see this dependence on enthalpy, temperature, and entropy. So one of the big things is if I'm going to go ahead and look at the, say, Gibbs free energy of an individual species, we're going to typically report these at a standard state temperature of 25 degrees C. However, we want to know what will happen to that free energy if I increase or decrease the temperature. Now, one of the big rules here is that, remember, if I'm looking at an individual substance, what I'm caring about is going to be my third law entropies, which by definition are always going to be positive because every substance has some degree of disorder. So as a result, what ends up happening is if temperature goes up, the Gibbs free energy will go down. So the system will actually become more favorable. And again, it is going to be worth noting that if you're assuming relatively small temperature changes, so less than 100 degrees C or Kelvin, we're going to treat entropy and enthalpy as relatively constant. In truth, you'd have to bring in heat capacities, but it's not bad. So in this case, I can treat my entropy as relatively constant. So if I increase the temperature, Gibbs will go down, and it will go down exactly by the value of entropy. And this is really what those units of entropy will tell me. The joules per mole Kelvin tells me how many joules per mole my Gibbs free energy will decrease if I heat up the system. So this actually helps bring in some insight. However, most of the time, I'm not so much focused in on the Gibbs of an individual species, because that is a little bit of an artificial value, as demonstrated by the fact we often use Gibbs of formations. What I really care about are Gibbs of reactions. So if I'm dealing with the Gibbs free energy of a reaction, now I have to bring in the enthalpy of reaction and the entropy of reaction. Now, one of the biggest reasons this differs is that turns out the entropy of reaction could be positive. I could be making the system more disordered, or it could be negative. I could be ordering the system. So in this case, now now the influence of temperature is going to be a lot more important. So if I'm going to be trying to figure out the favorability of a reaction, now enthalpy could be positive or negative, entropy could be positive or negative, but temperature will always be positive. And as a result, as I increase temperature, what we're going to see is that whatever sign entropy says is going to matter more. If I'm at low temperature, then this second term matters not quite as much, and this first term dominates. So let's go ahead and look at a couple examples. So let's say I have a system that is endothermic. So this means that it takes energy to go forward. Well, let's say that this same system has a negative change in entropy. So the system has become more disordered, more ordered. So in this case, it doesn't matter what the temperature is, because if I have a low temperature, this term dominates, I have a positive Gibbs free energy. Let's say I have a high temperature, then the second term dominates, and I have negative times negative, a positive free energy. So no matter what, if enthalpy is positive and entropy is negative, a reaction will always have a positive Gibbs free energy no matter what. So look for this pair. This is a way to tell that a reaction isn't spontaneous and never will be. And these are very important reactions to identify. And it turns out a good example of some of these are reactions like, photosynthesis. There's a reason you have to put so much energy into photosynthesis, because it requires heat to go forward and it orders a system. That is not a good double combo. So let's go ahead and look at the other end. Let's assume that a system is exothermic, so it generates heat and it's becoming more disordered. So in this case, it doesn't matter what the temperature is, because this sign says the reaction should go forward, and this sign says the reaction should go forward. So no matter the temperature, this reaction always goes forward. So think about reactions like combustion. As long as you give it enough energy that the reaction starts to occur, it goes forward very quickly because it's always going to be favorable. So these are going to be reactions you should always keep an eye out for, because this reaction will generally always be unfavorable or favorable no matter what. However, things get a lot more interesting and a lot more complicated if enthalpy and entropy share a sign. Because when these two values share a sign, this means they disagree about whether or not the reaction should occur. So let's go ahead and first focus in on what happens as I start changing temperature in one of these cases. So first of all, enthalpy is going to have relatively little change with temperature. So it's going to stay relatively constant, whether it's positive or it's negative. So let's go ahead and review one of those cases. So let's say that I've got a negative, I have a negative enthalpy, so an exothermic reaction, and I have a positive entropy. Well, in this point, the reaction at very low temperatures is favorable, and it just becomes more and more favorable the higher the temperature gets. So these are actually kind of cool systems. However, as soon as my signs are the same, we start getting into this second case where it's a lot more interesting. So let's go ahead and start with this blue line where I have a exothermic reaction. The reaction generates heat, so the reaction is favorable. However, let's say that it also ends up ordering the system. So this would be something like the dehydration of copper sulfate. So it turns out that this reaction will have a negative entropy as I'm going to be ordering the system, as I'm ruining this beautiful mixed matrix. And as I do so, what ends up happening is that the higher and higher the temperature goes, the more and more positive my Gibbs free energy goes. So in this case, what we end up having is the reaction ends up only being favorable at low temps. On the converse side, let's say that a reaction is endothermic. It doesn't want to happen. So this would be something like the melting of ice. At low temperatures, you won't melt ice. But as you add in energy, then the fact that the reaction wants to end up disordering, it has a positive entropy. I heat the system, and then it becomes favorable at these high temps. So in general, the big lesson here is that at low temps, the system does whatever enthalpy says, and at high temps, it does whatever entropy says. However, that leaves us to a very cool point right here in the middle, when the influences of temperature and entropy end up being equally dominant. So this would be when the system becomes reversible, or when it reaches equilibrium. So at this point, delta G equals 0, and both reactions happen equally. And this is going to be a very cool point we're going to talk a lot about in the future. We know this as things such as melting points or boiling points. So in this case, that boiling point or melting point can be calculated by taking the ratio of the enthalpy divided by the entropy. Using that, you can find whenever a reaction's at equilibrium. However, it turns out temperature isn't going to be the only thing that controls when equilibrium happens. Turns out pesky entropy plays a role again, and entropy depends on concentration. So next time, we're going to figure out how the favorability of reaction is controlled by the concentration of our reactants and products. Until then, take care.